Deep Belief Networks, DBNs, introduced by Geoffrey Hinton and his collaborators in 2006, marked a significant milestone in the landscape of artificial intelligence, AI, research and practice. These probabilistic, generative models have had a profound impact, providing novel insights and breakthroughs in various domains, particularly in the realms of machine learning and neural networks. We will delve into the fundamentals of deep belief networks, exploring their architecture, training process, and the transformative influence they've exerted on AI. Deep belief networks are a class of artificial neural networks that combine the power of unsupervised learning and deep learning. Geoffrey Hinton, a pioneer in neural network research, introduced the concept in a paper titled A Fast Learning Algorithm for Deep Belief Nets along with Simon Osendero and Yi Tay. At their core, DBNs consist of multiple layers of stochastic, latent variables, with connections between layers representing learned dependencies. DBNs are typically composed of two main types of layers: a visible layer representing observed variables and hidden layers capturing latent representations. The architecture is reminiscent of a restricted Boltzmann machine, RBM, with a stack of RBMs forming the layered structure. RBMs serve as the building blocks, modeling the joint distribution of visible and hidden variables. The first layer of the DBN, called the visible layer, receives input data. The subsequent layers, known as hidden layers, capture hierarchical abstractions and representations. The connections between layers are undirected, allowing for bidirectional information flow during training. This architecture facilitates the extraction of intricate features from raw data, enabling the network to learn complex patterns and relationships. One of the key innovations that set DBNs apart is their efficient training algorithm, known as contrastive divergence. This algorithm enables the unsupervised learning of hierarchical representations in a layer-wise fashion. The training process starts with the bottom layer, training an RBM to model the distribution of visible and hidden units. Once trained, the activations of the hidden layer become the input for the RBM in the layer above, and the process is repeated. The layer-wise training mitigates the challenges associated with training deep networks, commonly known as the vanishing gradient problem. By initializing the weights layer by layer and fine-tuning the entire network, DBNs overcome the difficulties in training deep architectures, paving the way for the exploration of deeper and more complex neural networks. DBNs have been instrumental in advancing the field of representation learning. The hierarchical feature learning facilitated by DBNs allows the network to automatically discover meaningful representations of input data. This capability has been leveraged in various applications, including image recognition, speech processing, and natural language understanding. The introduction of DBNs addressed long-standing challenges in training deep neural networks. The layer-wise training strategy, coupled with contrastive divergence, provided a breakthrough in mitigating the vanishing gradient problem. This opened the door for the development of deeper architectures, allowing researchers to explore more intricate and expressive neural network designs. DBNs have significantly contributed to the prominence of unsupervised learning paradigms. The ability of DBNs to learn from unlabeled data, capturing underlying structures and patterns, has been particularly valuable in scenarios where labeled training data is scarce. This has implications for real-world applications where obtaining labeled data can be resource-intensive. The pre-training phase of DBNs has been harnessed for transfer learning. By pre-training a DBN on a large dataset and fine-tuning it for a specific task, The network leveraged the knowledge acquired during pre-training. This approach has proven effective in domains where obtaining labeled data for the target task is challenging, underscoring the versatility and adaptability of DBNs. DBNs have been particularly successful in image and speech recognition tasks. The hierarchical feature learning capabilities of DBNs allow them to automatically extract relevant features from raw data, contributing to the state-of-the-art performance in these domains. The ability to capture intricate patterns has led to advancements in facial recognition, object detection, and speech-to-text applications. In natural language processing, NLP, DBNs have demonstrated their effectiveness in learning semantic representations of text. This is crucial for tasks such as sentiment analysis, document classification, and language modeling. DBNs, with their ability to capture hierarchical structures in data, have played a role in enhancing the understanding of context and meaning in textual information. The application of DBNs extends to healthcare and biomedical research. In areas like genomics and medical imaging, where the data is often high-dimensional and complex, DBNs have shown promise in automatically extracting relevant features for diagnostic purposes. The ability to learn meaningful representations from raw data is particularly valuable in these domains. Despite their remarkable success, DBNs are not without challenges. The training of deep networks remains computationally intensive, and issues related to interpretability and explainability persist. Ongoing research aims to address these challenges and further refine the capabilities of DBNs. Additionally, the advent of more recent architectures, such as convolutional and recurrent neural networks, has expanded the toolkit for deep learning, prompting exploration beyond traditional DBN architectures. In conclusion, deep belief networks, introduced by Geoffrey Hinton in 2006, have left an indelible mark on the landscape of AI research and practice. Their innovative architecture, coupled with an efficient training algorithm, has overcome historical barriers in training deep networks and has facilitated breakthroughs in representation learning. The impact of DBNs is evident across diverse applications, from image and speech recognition to healthcare and natural language processing. As AI continues to evolve, the foundational contributions of DBNs endure, shaping the way researchers approach complex learning tasks and inspiring further advancements in the field.